Ring is this company that basically builds security solutions for your home. It was actually started by, I believe, back in 2011 by our inventor Jamie Siminhoff, who was basically doing some stuff in his garage, and basically he noticed that whenever he was working in his garage developing new products, he started missing package deliveries. So basically he hooked up a small solution where he created this doorbell using Wi-Fi that he could basically see what is happening in his Porsche. And he started developing this product in 2012. The first product was released named Doorbot. And so on, and then it is actually quite fun because now you take it as a granted that you have this doorbell that you can pick up the phones, then you can pick up calls on your phone and see who is on your porch at your entrance. Back then it was totally new. It was the first product to actually use, to call to your mobile phone using as an IoT device. In 2013, he appeared on Shark Tank, this famous US show that is also in the UK, basically pitching this idea on live television. He did not get any investment, but obviously it brought him publicity, and the sales skyrocketed. And finally, in 2017, was it, or 18? Sorry about that. Amazon bought Ring, and we started expanding. So it's quite a nice thing about Poland that now we have a massive development center in Poland where we develop Ring both on the hardware side but also on the science side where I actually work on. So just to kind of show you off like what we have. Yes, with Ring, we say our motto is with Ring you are always home, meaning that whenever you want to see what is happening in your home, you can always pick up your phone and, I don't know, chat with the delivery guy or basically see how your dog is doing, which I actually do quite from time to time. And yeah, as I said, I am part of a data science team based in Warsaw, and what we do, so it's quite actually funny because we have something called Ring AI, which is doing basically everything related to computer vision on the device. This might be a package detection, and as a data science team, we actually do everything except what people do in Ring AI. So we have a quite massive lineup of products, starting from product recommendation to customer segmentation, a massive amount of analytical jobs, but we also start playing with LLMs and so on. And the best part is only a team of 4 people. So we have our manager and Kuba, who is actually sitting here, and the other guy. So only 4 people in Warsaw, and we have quite a massive lineup of products that is powering Ring business. And as a scientist, this is, you face a lot of challenges, and by the name of this talk, you might actually, one of the challenges that we have is that we, as a team, we do not have access to the recordings. We don't know what is happening on the client side. We don't have access. So, as a scientist, you might start doing contribute with new features. So you might start thinking how you can actually improve the product. And obviously, one of these things that you want to work on are videos. But the question is then, okay, if we don't have access to the videos, like what we can do actually? How you can create new segmentation models, classification models, if you actually don't have data to train on. So yeah, basically the next part of this talk is gonna be about this problem, like what you do if you don't have access to the data to train on. So yeah, as I said at the beginning, this part was actually, of the paper was done when I was a PhD student back in Edinburgh. So yeah, a massive shout out to the co-authors, Virginia, Pedro, and Walter, who were leading the paper, as well as my supervisor, Sotos, and Jorge, the supervisor from the King's College London. And yeah, I should say this, that also I was doing a PhD in medical AI, so what you're gonna see next has nothing to do with natural images of cats and dogs, but with medical imaging. So if you don't mind raising your hand, have you ever worked with medical data? Nice. So yeah, oh, it's not working, lovely. So it's obviously why we all do medical data and medical AI is that obviously we have this problem of aging population and growing pressure on the diagnostics. So obviously what we want to do is go to AI and develop a new tool, whether it's, I don't know, classification of diseases or radiology report generation. Basically, we want to kind of offload the healthcare system with some smart techniques. But we all do data, and obviously the data is the fundamental building block in creating such solutions. So the thing is, it's not in the medical domain, it's not like with ImageNet that you can actually go and download, but there is a massive amount of problems that you need to face in the first place before even you get access to the data. So the problem that we have similar is that, okay, like you are this amazing startup, you are a PhD student, how you actually get your hands on from the data from hospitals onto your desk. And the problem is that, well, it's not that easy because there's this privacy barrier that you need to go through in the first place. And what I mean by this privacy barrier is mostly about this risk of re-identification of a patient. So yes, sharing data is so challenging, but it's for the good reason. You need to go through quite a few questions, like ethical one. If it's what is the cost of sharing this data? If a patient might be, I don't know, re-identified, does it, cover the cost of helping actually people, speeding up the process of medical diagnostics? So, it's quite good that in the medical domain we have those few legal challenges that we need to go through, like GDPR in EU and UK and HIPAA in the US. So we need to go through those ethical and law-related questions to go first. And yeah, just as an example, what is personal data? According to UK's GDPR, is basically any information that can lead to identifying a patient or natural person, a subject. So the question is basically how we can still share the data, but avoid disclosing the patient. And yeah, as I said before, like we want to push the boundaries of the medical AI. We want to create new methods. We want to help the NHS or any hospital in the world. But medical AI needs data. This is quite obvious. And if you're gonna see on the stats, if we have access to Chinchilla, which is like 1.4 trillion tokens to create a new LLM, or Stable Diffusion that use 5.8 billion of image text pairs. Now, the biggest dataset, imaging dataset available for healthcare AI has actually 1.35 million. And funny story, when I was on the WWW conference, I believe 2 years ago, someone from Google actually told me just to change my PhD topic because it's not possible to do multimodal learning with this amount of data we have. So the problem is big. And also, on the other side, it's quite good that we also see this growth of FDA-approved AI medical devices. But again, it would be lovely to actually see this number skyrocket. But again, the access to the data is the problem. So as I said before, one of potential solutions we can have to actually solve this problem is to actually start creating this synthetic data that the hospital that has access to patient data could actually, for example, give fake data or a model to other parties that are interested in developing new models, such that there is no risk of actually identifying the patients. And obviously, we have GANs, we have Stable Diffusion, amazing models that create those realistic-looking images. But there is one but. We actually seen this, that if you have this distribution shift, if you have a super small number of samples, those networks tend to memorize well the samples. So even if you try to, be careful about how to strip the personal information about the subject, like, I don't know, removing the name of the ID of a patient, it's still, there is this case that maybe there is this kind of nuance in the imaging, maybe a disease that is so rare that the network will memorize. And now you have a problem. You have a problem because now this network is basically holding in the weights patient information. So what my colleagues and I try to tackle is this problem. How we can actually start doing this synthetic data, but not expose patient information. So with this paper, there are kind of a little bit, a few assumptions that I'm gonna through, but kind of our setup is, yes, we're gonna use the biggest text-image dataset in medical AI, which is Mimic-CXR. If you don't know, Mimic-CXR is basically X-rays of your chest, and they are coming from Harvard, I believe, hospital, and MIT, thank you. Even better. So we have those image experts where we have radiology reports. If you have never seen a radiology report, we have something called an indication. Basically says why a patient is going for a chest X-ray in the first place. Maybe, I don't know, they are coughing, or you want to check out if the device placement is done correctly. Then you have something called findings, which is basically saying what I can see as a radiologist on the picture, like everything I can see. And then finally we have impressions, which is basically the summary of the findings that might actually, for example, answer to the given question in the indication field. Is the placement correct? As a model, we use latent diffusion model because they are the state of the art and they are quite cheap. Nothing fancy, to be honest, a VAE with a diffusion model on top of it. And as I said, we do a conditional image generation, so we condition this on the impression. We say what we want to basically see on the image, and the network is generating that. And as the evaluation of what we actually, if our work was actually any good, we do downstream classification, so we basically classify if we can find those diseases, FID, and also what we introduce as re-identification ratio, meaning that from the whole population of images that we have, how many of those were re-identified to a patient. So first question we have is, okay, so we have some data set that is coming from real patients. We're gonna train a diffusion model that will start creating synthetic data. The first question we need to actually answer is how we do the retrieval. How we actually say that, okay, for this given image that we produce from the diffusion model is actually corresponding to these patients. So how we measure the distance between the real and the fake. And obviously, in the literature, you're gonna find that, yes, you can actually use simple metric like MSE or the quality of the image like FID and so on. But those metrics do not answer the fundamental question. Did we forget patient information? So the first question we need to answer is, okay, so if we cannot use those well-established metrics, how we actually say whether, I don't know, between 0 and 1, yes, 1 it means that the patient is basically the same, and 0, now there are two different patients. Of the generated image does not contain patient information from the real image. Oh, lovely. So what we actually do is, there is this quite interesting paper in scientific methods, scientific methods by Packhauser from 2022. And what they actually have done is remarkable simple network, which is basically a ResNet, where they basically say, okay, if I'm gonna give you two images, can you predict whether those two images come from the same patient? Quite simple setup. And what they have shown that they can basically get an AUROC of not 0.9994 or something like that. So basically, you know, they create a network that is extremely well doing on identifying the patients. And what is quite weird, well, maybe worrying, is that they also compare with images, I don't know, from 5, 10 years after the first initial image was presented to the network. And they also shown that, yes, network can easily identify that even after 10 years, after different diseases, after changing the, you know, the structure of your body, the network is still able to basically predict, yes, this is the same patient. So there is something basically there. So we have decided that as our metric, whether, you know, we can identify a fake image or synthetic image coming from containing identifiable information, is basically we use this network to basically tell us whether those two images come from the same patient or not. Yeah. Yeah, so you give basically imaging to the branch, and you predict whether it's the same binary classification, whether it's the same patient or not. So we actually, so in the paper, I don't remember the paper, but we actually, so we are working on the mimic CXR. We took this network and basically we upsampled the positive pair. So obviously in the mimic CXR, I believe you have, I mean, in the mimic CXR, sometimes you have just one scan, which is taken by a patient. Sometimes you have even 5, 10 scans. So basically we upsampled the pairs just to have this 1-to-1 ratio to the network, and we also got this 0.9999 AUROC. So, so yeah. So we also run a GradCam. Obviously, like we want to. I mean, GradCam is maybe not the best tool, but this is, let's say, it's good enough to see what is what does it mean identifiable by this network that I just presented to you. And we run on the embedding space, and basically what you can, I don't know if you can clearly see, but you know, basically the high score, you can see that the score is almost almost 1, meaning that the patient is, you know, this, I mean, it's identified by the network to be the same as the real image. And as you can see, like if you just eyeball by the way the lungs are seen on those images, you can basically see there is indeed some similarity between those two images. And then, you know, we have those few places that basically are saying, yes, this is the signal that was basically memorized by the network to reproduce. If we're gonna go down to that, yeah, the patient is different, it's actually funny to see that, you know, the GradCam says, well, this is the signal that basically help us decide this. And it kind of looks like a pacemaker. So, you know, you can basically hypothesize that, yeah, on the real image, you can see the patient does not have a pacemaker, and now we have some cables inside. So we might assume that those are 2 different patients because there's no pacemaker. Kind of a stretch, but I'm gonna take it. So yeah, I established that we have this network that is basically saying whether the patient is the same or not. Now what we do? Well, we produce tons of data, synthetic data, and we use this network to say, hey, okay, if some threshold, if we exceed some threshold, we discard the synthetic data and we say, well, we are not gonna share them. You can re-identify the patient from the real data set. So just that. And from those folks who are interested in the attacks and the leakage and privacy, please do check out this paper by Maria Jegorowa. She was actually a postdoc student, She was a postdoc in Edinburgh and done amazing work on inference attacks. In our case, we do not treat this as an attack because we still have access to the data, to the real data set, so we can basically compare whether the patient, the real patient, is still in the synthetic data set. So, and yeah, the second thing is obviously we want to improve. So we have this conditional latent diffusion model that we put impression, like what we want to see on those images, and obviously we need to check whether those images correspond to the given conditional impressions. So what we actually do is we use this lovely model from Microsoft, BioVille, which is this multimodal network pre-trained with a vocabulary on the scientific corpora, as well as also trained on the mimics nose and mimic CXR. So, you know, we align our vocabulary and we use this network to basically calculate to get the embeddings both for the image and the text, and we just take a cosine similarity to say whether, you know, those two are aligned. So again, nothing fancy to be honest, but good enough since this is the state-of-the-art now method for that. So now some simple stuff. So on the left-hand side, the first number is showing you whether the patient can be re-identified using this re-identification model. The second one is basically say how much the given image that was produced is aligned with the given text. And yeah, in the green boxes, you can see what we consider as accepted on the in the red boxes that we got rejected. What we do is basically we found a threshold 0.5. We did actually, it's not 0.5 because we were too lazy. We did actually experimental work, and basically between 0.05 and 90, it was basically the same. So we just said, okay, let's threshold everything at 0.5. And what we do for each image, we create 10 synthetic images. We re-rank them according to the, obviously we remove all those who can be re-identified. And then we take the image that has the highest alignment score between text and the image. So yeah, few examples that you can basically see. And I mean, if you are not even a radiologist, you can see that, you know, there is something odd with the quality of the images. And it's quite interesting because Mimic CXR was actually done in ER. Therefore, sometimes you might have patients so ill, so weak that you cannot get them to an X-ray examination room. Sometimes you need to bring the X-ray machine into the bed and take a picture. So then you will have those kind of really bad quality images like this one. And it's quite, you know, it's fun to see that, yeah, the network is actually trying also reproduce those patients who were taken, whose imaging exam was taken in a bad condition. And the screen is gone and it's back again. So yeah, after you get rid of the images, you basically create this new data set that has only filtered out data, and now we can have some stats about the score. So in the blue lines boxes, you have basically the data set that was not filtered out. So, you know, the synthetic data as a full. And then the orange box is after removing using the identification threshold. So as you can see, you know, before doing this easy, you know, threshold thingy, you get as well as not identified, but also as identified patients. But with, you know, if you just get rid of, obviously, with a threshold, that you get almost, I mean, yeah, almost non-identified patients. And then, sorry about that. And then you can see this is BioVil score. So this is how well the text and images are aligned with each other. And as you can see, it's quite interesting to see if you're gonna get rid of those patients who are re-identified, the alignment score between the images and the text actually improves, which is quite interesting. And yeah, why we did that, why the whole work was. Basically, yeah, because you get this this network that was, yes, network. So basically, you start training a network on the fake distilled data, such that you can do new stuff like classification, anomaly detection, or fine-tuning on a smaller data set. So basically, what we propose is you become a provider of the data that you should be more than happy to contribute to everyone without a risk of leaking identifiable data. So obviously what we did is, okay, we have this fake data, we have the real data, how does it work on the classification? So we take classification as, you know, as our benchmark, whether we did any good work or not. And it's actually good to see that if you train a classifier on the real data, okay, you get this AORC of 0.86 across all classes. But if you just use this distilled data set, so all fake, no identifiable samples in the data set, then obviously you get a performance drop, but it's not that bad. It's not collapsing. So yeah, quite good results. And lastly, yeah, so I'm with Ring, and I work with amazing people that if you're gonna spot them, you're gonna spot only Kuba is with me today. But please do talk to us, chat with anything you might have. We have also booth just around the corner. We have on Sunday a tutorial on how you can bring your idea into a full working solution with AWS. And yeah, thank you, amazing. That's all I have. So if you want to check out our posting jobs and stuff, please go ahead and scan the QR code.